Hi, my dear students. Now I'm going to give a video lecture on Laplace transform. Here, basically, we're going to discuss about introduction to Laplace transform, a review of complex numbers and complex functions, Laplace transformation, inverse Laplace transformation, partial fraction expansion with MATLAB, solving differential equations, and so on. The main cause to invent the Laplace transform is due to Pierre Simon Laplace. He developed mathematics in astronomy, physics, and statistics. Began work in calculus, which led to the Laplace transform. He focused on later on celestial mechanics, one of the first scientists to suggest the existence of black holes. Regarding the history of the transform, earlier, Euler began looking at the following integrals as solutions to differential equations in mid 1700s, like z is equal to integral x power x e power x dx, and so on. Afterwards, Lagrange took the step further by working on probability density functions and looked at the forms of the following equation like x of x e power minus x e power x dx. And finally, in 1785, Laplace began using a transformation to solve equations on of finite differences, which eventually led to the current transform like S and Ys and so on. Why do we use Laplace transform? So if you put a question like this, the main things are the following. Find a solution to differential equation using algebra. Relationship to Fourier transform allows easily to factorize systems. No need for convolution of input and differential equation solution. Useful with multiple processing system. Next, how to use Laplace transforms. Find differential equations that describe about the system. Next, obtain Laplace transform. Then perform algebra to solve the output or variable of interest. And lastly, apply inverse transform to find the solution. So the main process what I have already discussed is given pictorially like this. So Laplace transform is a powerful technique that replaces operations calculus by simple operations of algebra. So Laplace transform is a powerful technique that replaces operations of calculus by simple operations of algebra. And you see that here we have the ordinary differential equations with initial conditions, and you apply the Laplace transform and transform into simple algebraic equation and solve the simple algebraic equation. After getting the solution, apply the inverse Laplace transform, then we will get the solution to the required differential equation. This is also the same things regarding the how to apply the Laplace transform. You see that Laplace transformation from time domain. From time domain to Laplace transform to frequency domain and then solve algebraic equations and frequency domain known as FOS, the Fourier transform or the Laplace transform actually, and you apply the inverse transform to get once again back to the original domain, which is going to be f of t. Next, Many practical engineering problems involve mechanical or electrical systems acted upon by discontinuous or impulsive forcing terms. For such problems, the methods described are already are difficult to apply. To convert a problem for unknown function f into a simple problem for f, solve for f, and then recover f from its transform f. Given a known function k of st, an integral transform of a function is a relation of the form f of s is equal to integral alpha to beta k s of k st of f of t dt, where alpha ranges from alpha and beta ranges from minus infinity to plus infinity. And here the k of st is called the kernel of the function. Now look at the definition of the Laplace transform, which is given as follows. Let f of t be a given function defined for positive values of t and is of exponential order. Then the Laplace transform of f of t is given by L of f of t. It is nothing but the integral 0 to infinity e power minus ft, e power minus st into f of t dt, and this is denoted by f of s, provided the integral exists. Here the parameter s is a real or complex number. So as I have already told, the kernel of the function is given by k of st is equal to e power minus st. So depending on the kernel, we will get different types of transforms. So I can say that basically Laplace transform is an integral transform, and therefore we can say that Laplace transform is a special case where the kernel is going to be e power minus st. Since solutions of linear differential equations with constant coefficients are based on exponential function, the Laplace transform is particularly useful for such equations. We note that Laplace transform is defined by any improper integral and thus must be checked for convergence. This is very important. On the next few slides, we review examples of improper integrals and piecewise continuous functions. So here integral 0 to infinity e power minus st f of t dt is equal to f of s, and therefore f of t is the function and e power minus st is the kernel here, and the kernel is acting on f of t, is giving the output as f of s, which is called the Laplace transform. So we say f of s is the Laplace transform of f of t. In other way, we can write L of f of t is equal to f of s, or I can say instead of f of t, if I am going to say a y of t, I will say y of s, or if it is going to be x of t, it will be x of s. Like that, we can represent the Laplace transform in many ways. Now, existence of Laplace transform, because we do not know that for all the functions and for all the domains the Laplace transform exists, but there are some conditions where it won't exist. So if you look at in that point, so there are two governing factors that determine whether Laplace transforms can be used. The first one is the function f of t must be at least piecewise continuous for t greater than or equal to 0. In other words, it must be positive values of t. And also, the modulus of the function f of t must be bounded, and therefore where m and gamma are constants. So then the Laplace transform, if these two conditions are satisfied for f of t, then we can guarantee that for such function, Laplace transform exists. So we are giving here L of f of t is equal to f of s, integral 0 to infinity e power minus st f of t dt. It must be finite. So a function that satisfies the condition, the special condition, what is called f of ft less than or equal to m of e power gamma t, where m and gamma are constants, is said to have exponential order as t tends to infinity. Next, regarding the continuity, since the general form of the Laplace transform is f of s is equal to integral 0 to infinity e power minus f of t dt, it makes sense that f of t must be at least piecewise continuous for t greater than or equal to 0. If f of t were very nasty, the integral would not be computable. Next, boundedness. This criteria is also follows directly from the general definition L of f of t e power integral 0 to infinity e power minus st f of t dt. If f of t is not bounded by the function m e power gamma t, then the integral will not converge. This is the second condition to be followed for the existence of Laplace transform. Now we'll try to calculate for Laplace transform for simple examples. Now consider the following, of course here, the following improper integral 0 to infinity e power st dt. Here we see that the integral is going to be 1 by s. When I do the integration, I am getting 1 by s limit b tending to infinity e power sb minus 1. And we know that if s is equal to 0, e power s is equal to 1, thus the following two cases hold. E power st dt is equal to minus 1 by s if s is less than 0, and e power st dt diverges if s is greater than or equal to 0. So you see that from this integral, from this example, there are some improper integrals which always won't converge. It may be in some conditions it is diverging. So in this example, you see that this integral is converging when s is less than 0, but it is going to be greater than or equal to 0 if s, it is going to be divergent. Consider another improper integral 0 to infinity st cos t dt. You evaluate the integral, and finally I'm getting limit b tending to infinity sb sin b plus s into cos b minus 1. Since once again here the limit diverges because sin infinity is infinity, therefore immediately this is also divergent. Therefore we cannot expect any Laplace transform for this function. Now, piecewise continuous function. A function f is piecewise continuous on an interval a comma b if in this interval can be partitioned by a finite number of points, a is equal to t naught less than t1 less than so on tn is equal to b, such that f of is continuous in each subinterval tk comma tk plus 1, and also the modulus of the function limit t tending to tk must be less than infinity, and also here for other values 1 to n also it must be less than infinity. In other words, f is piecewise continuous if it is going to be continuous except for a finite number of jump discontinuities. So consider the following piecewise defined function. You have f of t is equal to t square, 0 less than t less than 1, and f of t is equal to 3 minus t, 1 less than equal to t less than equal to 2, and t plus 1, 2 less than t less than equal to 3. So from this definition, f from the graph of f below, we see that f is piecewise continuous. Now you see that this in this interval is continuous, in this interval it is continuous, and in this, from 0 to 1 also it is continuous, from 1 to 2 is continuous, from 2 to 3 is continuous, but in between 1 and 2, we don't have any graph, therefore it is discontinuous. So that's why we say this kind of function is piecewise continuous. In a similar manner, this is another function which is also piecewise continuous. Now, take the example. Here f of t is equal to k, where k is a constant. Now we'll try to find the Laplace transform f of t, and f of t is given to be given by k. So therefore, k is equal to here. It is nothing but integral 0 to infinity e power minus st k dt. Here f of t is nothing but k, and that is equal to, you just integrate, it is nothing but e power minus st, e power minus st by minus s, and therefore k into, you just simplify this integral, I am getting k by s. And you take k is equal to 0, the Laplace transform of that function is going to be 0, and if k is equal to 1, it is going to be 1 by s. So this is a simple example where f of t is a constant function whose Laplace transform is given by k by s. Second example, we have f of t is equal to e power at for t greater than or equal to 0. Then you find the Laplace transform, and after using evaluating the integral, we are getting 1 by s minus a, where s is going to be greater than a. Therefore, the Laplace transform of f of t is equal to e power at is given by 1 by s minus a. Similarly, when you put a is replaced by 1 minus a, the Laplace transform of e power minus 8 is nothing but 1 by s plus a. Next example is f of t is equal to sin 80. In a similar manner, you can calculate by using the definition e power minus st. F of t is nothing but sin 80 dt. You just do the integration, and according to the integration, using the integration by parts, we am having, and ultimately by applying the limits and all those things, it reduced to a by s square plus a square, where s is greater than 0. In a similar manner, we can calculate f of t is equal to cos 80, and therefore we can write cos 80 as in terms of exponential function e power I80 plus e power minus I80 divided by 2 into e power minus st dt, and therefore by just integration using the cancellation property, immediately I will get 1 by s minus ia minus 1 by s plus ia, and simplifying these two I will get s by s square plus a square. In a similar manner, we can go for cos h80 by using the definition. I can say it is nothing but s by s square minus a square. And this is the results which we can give here, nothing but multiplication by t. So L of t into u of t, integral 0 to infinity, t into e power minus st dt. So here the function is going to be multiplied by t. And we are using the integration by parts, integral u dv is equal to uv minus, therefore I will get integral multiplication by t as 1 by s square, that is t into u of t. For this function, the Laplace transform is 1 by s square. Okay. Similarly, we can show that these transforms L of t power n is nothing but n factorial by s power n plus 1, and so on. Next property. So you have linear property, first shifting. So linear property is nothing but if f of t and g of t are two functions and a and b are constants, then L of a into f of t plus b into g of t is equal to L of a into L of f of t plus b into L of g of t. And the shifting theorem is nothing but L of e power at into f of t is equal to f of s minus a. That is a function of s minus a. So example f of t is equal to e power minus 2t minus 3 into sine 4t for t greater than or equal to 0. So I am using the linearity property here. Therefore, L of 5 into e power minus 2t minus 3 into sine 4t. I can write as I can take the 5 constant outside and L of e power minus 2t, and I can take 3 constant outside, and you find the Laplace transform for sine 4t. And using the exponential function on sine, we can find the Laplace transform is nothing but 5 by s plus 2 minus 12 by s square plus 16, where s is going to be greater than 0. So the formula what you have so far calculated, I can write it as, I can summarize like L of 1 is equal to 1 by s, L of t is equal to 1 by s square, L of t power n factorial by s power n plus 1, L of t power n into e power 80, and n factorial by s minus a power n plus 1, L of cos of t is equal to s by s square plus 1, L of sin t is equal to 1 by s square plus 1. So these things we have already calculated, and we have summarized all the results here. So in a similar manner, we can calculate the Laplace transform of different functions using the property of linearity. So L of 1 plus 2t minus t power 4 by 3. You can just using the linearity property, I can write L of 1 plus 2 into L of t minus 1 by 3 into t power 4, and apply, you know that L of 1 is nothing but 1 by s, and L of t is nothing but 1 by s square, and t power 4 is 4 factorial by s power 4 plus 1. Simplifying, I am getting 1 by s plus 2 by s square minus 8 by s power 5. So these are the results. Of course, Laplace transform of derivatives, transform of integrals, transform of multiplication, transform of division. This is Laplace transform of derivatives. L of f dash of t is equal to s into f of s minus f of 0. And transform of integral, L of integral 0 to t f of u du is equal to f of s by s. Multiplication by t f of t power n. L of t power n to f of t is equal to minus 1 whole power n, and it is d by d power n by ds power n f of s, and transform of division, L of f of t by t is equal to integral s to infinity f of u du. So this is Laplace transform of derivatives. We have to show that L of d of f of t by d of dt is equal to s into f of s minus f of 0. So this can be easily shown. And the next thing is we can say this is the proof part. We need not worry about the proof, and it can be continued like this. So in general, we can show that L of d f of t power n by dt power n is equal to s power n f of s minus s power n minus 1 f of 0 minus s power n minus 2 f dash of 0, and so on, f of n minus 1 0. So this is the result of what we have to use. So therefore, this is the Laplace transform of integral. So once again, this is the proof. We need not worry about the proof of those details. We only require the result. Therefore, the Laplace transform of integral is nothing but f of s by s. This is most important result we have to memorize. Next, convolution theorem, we can say that if f of t and g of t are two functions, then the convolution of f of t and g of t is given by integral 0 to t f of u g of t minus u du. This is the convolution. For some problems, it is very essential for us to find the convolution and then come back to the original results. So this is the Laplace table of Laplace transform. So far we are done. Del of t is equal to 1, u of t is equal to 1 by s, e power minus s t is equal to 1 by s plus a, t equals 1 by s square, t power n factorial by s power n plus 1. So this is continued. We have already calculated all these Laplace transforms. These are some things we have tabulated of different. These are the common properties. And we have initial value theorem. So the initial value theorem, it says if the function f of t and its first derivative are Laplace transformable, and f of t has a Laplace transform f of s, then the limit s tending to infinity s into f of x exists, then limit s f of s tending to infinity is equal to, so this is same as limit f of t tending to 0, and that is equal to f of 0. So the utility of this theorem lies not having to take the inverse of the transform in order to find out the initial conditions in the time domain. Especially particularly this is particularly useful in circuits and systems. So this is an example where we have initial value theorem, and we are given f of s is equal to this much, and we have to find f of 0. So you see, you are given the Laplace transform, and I have to find what is f of 0. And you take f of 0 is nothing but limit s tending to infinity s into f of s, and that is equal to s into s plus 2. This is I have to substitute here, and you apply the limit, and then since it is infinity, it is reaching the infinity, dividing by s square, the highest power in the denominator and in the numerator and denominator, and applying s tending to infinity, it will reach us 1. That is very simple. And final value theorem I have, which says if the function f of t and its first derivative are Laplace transformable, and f of t has a Laplace transform f of s, and the limit s tending to infinity s into f of s exists, then the same thing here, but only the thing is here it is a t is going to be the final value. Previously it is tending to 0, now it is tending to infinity, and the value is going to be simply you substitute in the function infinity and try to simplify that, we will get as the final Laplace final theorem. Again, the utility of this theorem lies not having to take the inverse of f of s in order to find out the final value of t in the time domain. So this is particularly useful once again in circuits and systems. Again, we have the same example, f of s is given and we have f inverse of s. This we can always find. So you find what is f inverse, apply the inverse Laplace transform, and if we are able to calculate that as t into e power minus 2t and cos 3t, because using the translation property, immediately we can calculate this, and we have to find infinity. So now you substitute f of infinity in this function. So if I find in this function, I'm going to get, so the value is just tending to 0, I'm going to get it as 4 minus 9, and once again s is 0 means 4 minus 9, this is 4 plus 9, 4 minus, so 5 by 13.